the red subscribe button right under the video and also the bell icon to get notification on any of our latest updates on our videos.
Hello everyone, welcome to Smart Guides Tutorials. Today we are going to solve a problem in solid mathematics 2. We have the problem of two parts before us. The first part says, derive the expression for the maximum deflection of a simply supported beam of negligible weight carrying a point load at its midspan position. The distance between the supports is L. The second moment of inertia of the cross-section is I, and the modulus of elasticity of the beam material is E. So let's start solving the first part, and we have solution. For the A part, we have a simply supported beam supports at the end, and it has a length L, that is the distance between the two supports, and a concentrated load W, midspan, or acting at the middle. So we are to examine the left part away from the load. Having a total length of L, dividing such length into half, we get L over 2. If this part is X, the remaining part will be L over 2 minus X. From the law of forces, it says the upward forces must equal the downward forces, and on the supports we have reactions of W over 2. Each is half the point load, so this implies is equal to W, so this part is verified. Next, we find the shear force at the section XX, because we are analyzing the cross section XX, and the shear force is given by W over 2. We find the bending moment after, and we know bending moment is the force times the distance from which it acts, which would be given by W over 2 times, and looking at the figure, W over 2, the reactive force, displaces a distance of L over 2 minus X from our cross section X. So therefore our distance would be L over 2 minus X. Our formula says M, the bending moment at a cross section XX, is equal to the modulus of elasticity times the moment of area multiplied by the second order derivative, and this, making the second order derivative the subject of the formula, gives us M all over EI, which is the modulus of elasticity times the second moment of area. For us to get the equation, we integrate the above expression, but before we integrate we have to put the value of M, which is given as W over 2 times L over 2 minus X, right, over EI. Next we do our integration. this is the same thing as 1 over EI times W over 2 into L over 2 minus X. So expanding this gives 1 over EI into WL over 4 minus WX over 2. During the first integration, we get the change in the deflection or slope to be equal to 1 over EI times difference. Integrating the expression WL over 4 with respect to X yields us WLX all over 4 minus WX, this would be squared over 4 plus A, where A here is a constant and it comes as a result of an indefinite integral with no range of values. Integrating this equation further, it yields us with y, which is the deflection, right, is given by 1 all over EI times WLX squared all over 2 times 4 is 8 minus W here would be X cubed all over 3 times 4 12 plus AX plus B here is another constant. So we have gotten 3 expressions. One, bending moment. The second is our slope or change in deflection. And the third is our slope. Next, we are to set the boundary conditions. Now, at the point where x is equal to 0, referring back to our diagram, for us to know where x is equal to 0, at this point x here is equal to 0. So for our first boundary condition, at such point where x is equal to 0, our change in deflection dy dx would be equal to 0. Our expression for change in deflection dy dx is equal to 1 all over EI times WLX over 4 minus WX squared over 4 plus A. What we are going to do here is we are to find the value of A. So substituting the values, we have 0 is equal to the reciprocal of E times I into 0 minus 0 plus A. This is because x is equal to 0. So we have A over EI to be equal to 0, and that implies that A is equal to 0. The second condition, at x is equal to L all over 2, that is from the point where x, from the diagram here, from this point where x is 0, it increases towards the left up to the time it will reach this very point. Let's name it Q. At Q, x is equal to L all over 2, that is half the length of the beam. So at such point, sorry, our deflection y would be equal to 0 because there would be no deflection at that stage. Our equation says y is equal to wl over 8. X here is said to be L over 2, 1 all over EI into WLX squared all over 8 minus WX cubed over 12 plus AX plus B. So substituting the values of x, y, and possibly a, knowing that a is equal to 0, we have 0 is equal to 1 all over ei into L cubed all over 2 times 2, 4, 4 times 8, 32 minus WL cubed over 2 times 2, 4, 4 times 2, 8, 8 times 12, 96 plus B. So this would be equal to 1 all over EI into this whole expression would be 3WL cubed over 96 minus WL cubed all divided by 96 plus B. B upon collection of like terms would be negative 2WL cubed all over 96, and we'd have B to be equal to negative WL cubed all over 48. So now we have gotten the values of our constants a and b. Next, what we are to do is we would substitute those values into the equation of our deflection y, which is equal to the reciprocal of e times I into w lx squared over 8 minus wx cubed over 12 plus a here, which is 0 times x, plus b, which was gotten as negative wl cubed over 48. So therefore our expression y would be equal to 1 all over ei into WLX squared over 8, right? Minus WX cubed over 12 minus WL cubed over 48. And for us to find the maximum value at x equal to 0, our maximum value, that is y, would be equal to y max, that is the deflection would be maximum, where x is at the point where the concentrated load is acting right here. Our maximum value for y at that point would be y max, knowing that x is equal to 0. Our y max would be WL cubed all over 48. So this is the expression for y deflection where it's maximum. For the B part, we'll meet in the next video. Thank you very much.